Hello everyone and welcome back to our channel Agnipunk. In this video we are going to start a new series on work done and energy. Okay, so in this video we are going through a few topics, a few basic concepts, and we'll be uploading several videos on this topic for the conception on the various parts, the various details of this topic, that is work done, energy and power. So in this video, we are going to discuss introduction, means what is work done and when do we say that is a work done, or why do we need to study work done, what is the significance of it, and when do we say there's a work done by a force, or the nature of the work done, whether the work is negative, positive, or zero. And finally, we'll be summing up with the topic work done by a variable force. What if the force is decreasing by time or increasing with respect to time? Okay, so let's get started. So almost all the terms we have used thus far: velocity, acceleration, force, and soon convey a meaning in physics as they do in our everyday life. Now we encounter a term whose meaning in physics is distinctly different from everyday meaning. Okay, that is work. Uh, in everyday life, when do we say we are going to do a work? Suppose our parents asked us to carry a box of mass m to some place, from some place A to some place B, and a boy, an obedient boy, what he does, he will carry that box to some place B. In general terms, what do we say? That the boy is very good, the boy is very obedient, and in general we'll say that the boy has done a work as he has carried that box of mass m from place A to place B. But when we are talking in concepts of physics, the boy hasn't done a work. Okay, the boy hasn't done a work on the box. Okay, so this looks a quite, means, strange, that we are looking that no, the work has been done, but still we are saying on the basis of physics that no work has been done. So starting with the first topic, that is work done by a force. When do we say the work has been done by a force? Okay, the first and foremost thing is, on an object of mass m, there must be a force applied. There must be a force applied, and there must be some sort of change in position. Okay, there must be some sort of change in position. Okay, so suppose we have a surface and a box is kept over it, and we are applying force. So there must be a change in position of the block of the mass. As you can see here, the box was here, and in the motion from going from place I to place F, sorry, xi to xf, a force of magnitude F is being applied to this body at an angle theta, which makes this box move from part A to part B. Okay, so in this case, what we have, we could say the work is done. And how do we say this? Work equals force vector dot displacement vector. Okay, you can see here, force dot displacement vector means this is a dot product. So we would say F S cos theta. Okay, means what? force in the direction of displacement. We have to take the force in the direction of displacement. If there is a force in the direction of the displacement of the body, we would say that work has been done. But when there is no force, there is no force in the direction of displacement. Suppose if the force was acting perpendicularly, if the force was in perpendicular direction, suppose the force was acting in this direction, and the box was moving in this direction. In this case, what do we say? That the force is acting along y-axis, and the displacement that is being observed in x-axis. So there is an angle of 90 degree in between this. And when we will be calculating this will be equal to what? F dot s into cos of 90 degree, and which equals 0, as we can say that there is no component of force in the direction of the displacement, or in the direction of the motion of the body. Okay, so this is the basic thing. Okay, so we have to do two things. First, resolve force vector in the direction of displacement vector, or we could do vice versa. We could also resolve the direction of displacement vector in the direction of force vector, but that is a different case. In that will be also a similar thing, or that will also be giving you a similar answer. Okay, so this was the basic thing. When do we say a work is done by a force? Means there should be a displacement in the direction of the force applied. Okay, there should be displacement in the direction of the force applied. Now, nature of the work done. When do we say that work has been done on a body or not? We would say a work has been done on a body when there is a displacement, okay, and when that work is positive, negative, or zero. Okay, so in first case, what do we have? In this case, the angle between the displacement vector, that is this vector, and the force vector is acute angle theta, and which is less than 90 degree. So in this domain of theta, what do we have? Cos of theta is always positive, is always positive. And if the magnitude of force and displacement are non-zero, if the magnitude of force and displacement are non-zero, and the theta is less than 90 degree, we would say that the work done is positive. Means what? The theta means the angle between the force vector and the displacement vector is deciding the nature of the work done. And in the similar manner, when the force vector is acting perpendicularly to the direction of displacement vector, in this case we would say that the work done is 0, as the theta between the force vector and the displacement vector is 90 degree. So in this case, cos of theta will be equal to 0, that is cos of 90, as we know. And in the similar manner, when the body is displacing in such a way that the angle between the force and the displacement vector is greater than 90 degree but less than 180. In this case, we would say that the cos of theta, cos of theta is less than 0, as in the domain of pi by 2 to pi, we say that cos of theta is always negative. Okay, so this was the basic concept of nature of work done. Negative work done when the theta is between pi to pi by 2. Okay, this is for the negative work done. For zero work done, we have theta is equal to 90 degree, and for positive work done, theta must be lying between pi by 2 pi by 2 to 0. Okay, so these are the conditions which decides the nature of the work done, means whether the work is positive, negative, or 0. Now the same case here, when do we say that there is a work done, or when do we say there is a zero work? Okay, so we have already seen where there is a work done, and in this case we'll be looking with a few examples of zero work done. Okay, suppose if a body is there and a man is applying force to it, a man is applying force to it, there's a body and the man is applying force to it, but this force is unable to give this block a motion or give this block some sort of displacement. In this case, in general, we say that no, the man is so work hard working and he is pushing that block to from a larger block, a larger block in comparison to his mass. He's doing a lot of work, but still, in the language of physics, when we are talking in the domain of physics, we would say that no work has been done, as we can say that there is zero displacement. There is a force, there is a greater force, but the displacement is 0. So in this case also we would say that no, there is zero work done. Or if the boy, the obedient boy, is taking that mass m to some destination b, in this case also the work done on the box, work done on the box is sort of 0, because the box, on the box there is a force of gravity acting downwards, that is mg, and the boy is giving a displacement in the perpendicular direction to the gravity. But if we say that work done on the box by the motion of the boy is 0 or not, so in this case we could say that no, there is some sort of work done, as there is the change of position, there is change of the position of the system. The system has displaced from point A to point B. The system has displaced from point A to point B, and in this case there is, as the boy was standing here, so the net velocity was 0 here, and at point B let us assume that boy will be having some sort of velocity, or the boy would have attained acceleration, some sort of velocity, let this a, okay, some sort of velocity, a meter per second. Okay, and there is a change in velocity, so we could say there must be some sort of acceleration. There must be some sort of acceleration. Okay, and if there is some sort of acceleration, the block has experienced some sort of force in this direction too. Okay, and there would be some sort of work done in doing this process. But if we are talking about the work done due to gravity, work done due to gravity, that will be zero. And at last, work done by a variable force. Okay, suppose the boy was doing a work on this block. Okay, he was pushing this block. He was pushing this block. Let us make this block first. He was pushing this block, and initially he was offering a force of 400 Newton. Okay, the block is quite big. After some time t, what happened? The boy got a bit tired. Now the force that is being applied by the boy on the box is sort of 200 Newton. Okay, and at last, after some 10t time, the boy is completely exhausted, but he is still sort of doing some sort of work. He is still applying some sort of work on the block that is giving this block some sort of acceleration. Sorry, displacement. And at this point of time, the force that is being applied is 50 Newton. So from case A to B to C, we could say that the force is decreasing with respect to time. The force is decreasing with respect to time. And in this case, there is a variable force. There is not a constant force that is being acting, that is being constantly acting on the boy, on the box, sorry, by the boy. There is a variable force that is being applied on the box by the boy. Okay, so in these cases we can't apply directly the formula F dot S. Okay, because we don't know, we at various point of time we have a different value of force. Okay, so we can't apply the same formula. So in this case, what do? We have a different step, we have a different method of solving this. We would do, we would consider a small work done, dw. Okay, dw by the force F at that particular instant, say. Okay, force applied at that small interval of time into the displacement because of that force. Okay, this will give you a sort of a small infinitesimal amount of work done. Okay, now what we have to do, we have to integrate. Suppose the box has moved from position A to position B. The box has moved from position A to position B, and here the x coordinate was, suppose x equals small a, x equals B. So in this case, what we'll say, that the work done is equal to, integrate, we'll be integrating both of these, and the limits that will be equal, that will be governed, that will be according to this part, this differential part, that is A to B. final answer would be whatever the integration would come, or we could say the area under the force and displacement graph. Suppose this was the work done, and this was the increasing force, and this was the displacement from point A to point B. So net work done will be the area under the curve, or under the equation of the force, under the equation of the force, this different integrated with respect to displacement vector. Okay, let us do an example. Okay, let us do an example for this. To make this concept a bit clear, a force a force of A plus bx acts on a particle in the x direction. A force, let this be x direction, and it is already our x direction, which displaces the body from position x1 to some position x2. Okay, mass is here, and the final time, this is here. Find the work done by the force during this displacement. Okay, so suppose the force is making a very small sort of displacement, because at some after some time this force will change to some other value as the x is changing. Let this displacement be dx. So this small work done could be written as dw is equal to f dot dx. Okay, but the box has displaced from x1 to some x2, means we have to go from here to here. There would be infinite number of times, infinite number of dx between these. Okay, we'll be summing up all the work done, we'll be summing up all the work done, and we'll be adding up all those. Okay, so in order to do that, we would do the integration x1 to x2. Okay, so integrating this, we have f, the value of f which is given as a plus bx into dx, limits x1 to x2. Now a dx x1 x2 plus bx dx x1 x2, this equals a dx integrates to x from a limit of x1 to x2, and b being constant comes out of integration, and x dx integrates up to x square upon 2, and the limits x1 to x2, which is equal to a upper limit, that is x2 minus x1, plus b upon 2 upper limit, that is x2 square minus x1 square. Okay, So the final answer is something like x1 minus sorry, x2 minus x1 a plus b upon 2 x1 plus x2. Okay, so this was the work done in this process from taking the box of mass m from position x1 to some position x2. So in this way we could solve the questions. Okay, so wrapping up this video here, and thanks for watching. You could follow us on Instagram, Telegram, and we'll be uploading the next video soon. You could suggest me the topics you wish to explore. Okay,